All right, so we have these complex values that are going to be part of our probability amplitudes for our states. So let's look at some complex phase on the Bloch sphere. So we looked a little bit at this last time. So we have our state ket I, which rests on the y-axis, and it's going to be in the positive y direction. And then we have the state negative I, which also lies on the y-axis, but in the negative direction. So we can see that we have a plus I phase in ket I, and then a minus I phase in ket negative I. Now, just a reminder, what is I exactly? I is the square root of -1. So how exactly do we calculate the probabilities for these states? We looked at previously when we were working at real values, we looked at magnitude squared, and it's the absolute value squared, and it's the same exact calculation, but we have to think about the calculation slightly differently when we're working with complex values. So when we have a complex value, we know that the absolute value or the magnitude is going to be equal to square root of z multiplied by the complex conjugate of z. So z here is a complex value. So we know that the probability for measuring ket 0 and ket 1 is just going to be taking those probability amplitudes and taking their absolute value and squaring them. So whenever that's a real value, we just square that probability amplitude. So let's see how that changes slightly when we're working with complex values. So we're going to examine I, and we'll have to use this application of the complex conjugate in order to come up with the value for the absolute value before we square it. So let's look at that. So take as a note, when we have I times I, that's going to equal -1, and negative I times I is going to give us a +1. So once again, we kind of tie in that whole idea that even though we're working with imaginary values, we're able to operate on them and produce very real values. And those real values are going to be our probabilities of either observing a ket 0 or ket 1. So for the probability of ket 0, we are going to take the absolute value squared. So that will be for us a 1 over square root of 2. So 1 over square root of 2. We take the square root of that and square it. So we can simply just kind of cancel out these two operations, the square root and squared. That gives us a calculation of 1 over square root of 2, which gives us 1/2. Very similar to the operations we've been implementing this whole time with real values, because the probability amplitude associated with ket 0 is a real value. Now let's check out probability of ket 1. So here's where we kind of get a little bit trickier, because we have to think about what we do to that imaginary value so that whenever we use it in our calculation, we can produce a real value from it. So we have the absolute value of beta squared, which for us is going to be I over square root of 2. So we have I over square root of 2. We want to take that complex conjugate, so negative I over square root of 2. We multiply our i's together. So we know negative I times I is going to give us a 1. So we have 1/2 squared, and then a square, or we have 1/2 square root and then squared. So that will give us a 1/2 once again. So even though we had an imaginary value in that probability amplitude, we were still able to get a real value for our probability associated with ket 1. All right, so now we're going to talk about applying these different operations into rules that we have associated with qubit basis sets. So we talked about whenever we're looking at basis sets for quantum computing, the ones we defined were on opposite sides of the Bloch sphere. And why was that? Why were they on opposite sides of the Bloch sphere? So we had ket 0, ket 1 at the North Pole and South Pole, respectively. We have ket plus and minus on the front and back of the Bloch sphere. The reason why they're on opposite sides is because they're orthonormal. So orthonormal, orthogonal, and normalized. So orthogonal, so we want to make sure that they are perpendicular. So we apply this operation of inner product in order to make sure that the two vectors that we're working with in our basis state are equal to 0, so they have no overlap. We want to make sure that we use two orthogonal vectors that together we can describe any point in our space, but they do not contain any other, one of those vectors doesn't contain any portion of the other. So we want to make sure that our basis vectors, one is not a multiple of the other, so that they're orthogonal, they're perpendicular from each other. So this is our first rule that we have associated with basis sets. So here we're going to apply our inner product and our bracket conversion that we implement using the conjugate transpose. Second, we have to make sure that each vector has a norm or distance of 1. So that might sound a little confusing, but we've been working with this the whole time. We have to make sure that all of our probabilities, they have to sum to 100% with the quantum state. We have a 100% chance that we're going to be either in ket 0 or ket 1. So we take the inner product here, and that is going to be equivalent to the magnitude of a particular vector. So we want to make sure that the absolute value is equal to 1. So we look at that. What does that look like when we're working with real numbers? The absolute value is just going to be, and another name for that is called the Euclidean distance. So the absolute value is going to be, so we take every element, if it's a real value, and take the square root, or we take a probability amplitude and multiply, or a vector component and multiply it by its complex conjugate. So this looks like a lot of information, but we're going to test it out and show that our basis vectors are orthonormal and they have a distance of 1. So we're going to check orthonormality for our computational basis. So we have to make sure that included vectors are orthogonal and perpendicular. So we're going to check to see that we have our probability amplitude. So we want to take our vectors. So here we have ket 0 and ket 1. So as a reminder, we have to take the conjugate transpose of that ket 0 to turn it into a bra 0. So we can do our inner product operation. So that'll convert the column vector into a row vector. And then we simply do our vector multiplication. So here, since we have a row vector and then a column vector, we're just going to do row times column. So that'll give us a 1 times 0 plus a 0 times 1. So that'll give us a 0. So all included vectors are perpendicular here. We know that we have two linearly independent vectors. One is not a multiple of another. So that has been confirmed by this inner product operation. Next, we have to check that each vector has a norm or a distance of 1. So once again, we're going to be applying that inner product. This time, we're going to do the multiplication with the inner product of each vector with itself. So we have to make sure that it has a absolute value of 1. So we can check that here. We have bra 0 inner product with ket 0. So we look and we do our element-wise multiplication because we do row times column. So here we have a 1 times 1 plus 0 times 0. That gives us a 1. Now we're going to test this out with our basis state ket 1. So we take the conjugate transpose of that. That's going to become a row vector. So our element-wise multiplication. So we have 0 times 0. 1 times 1, that results in a 1. So we confirm that we have orthonormality with our computational basis. So just to point out, whenever we're doing these calculations, the orthogonal component of these rules, that is done with each vector times the other vector in the basis set. So these are two different vectors. So ket 0 and ket 1 will be included in that calculation. When we're checking for distance, that's going to be each vector compared to itself. So we want to make sure that each vector, the inner product is equal to 1, and that simply means that each vector has 100% probability associated with it. So we want to make sure that that inner product is equal to 1. And then with those basis sets, you can express any state in your system, in your quantum system. All right, so are there any questions?